Yeah, yeah. Oh, no way. Yeah, I think we met briefly before. Yeah, and also he was in San Francisco. A CodeCon thing. Okay. Oh, okay. Cool. Yeah. Yeah, yeah. Okay. Oh, okay. All right. Start. Um, this is. Oh, first of all, did people get drinks? Everybody got the memo about the drinks, about the bar and stuff. You didn't get a drink. Okay, I'll bring you back a drink in a minute. What do you want to drink? What do you want to drink? A beer or Corona? Okay, great. So, yeah, Dan will be starting in just a minute here. Uh, he's working on some pretty cool stuff with FPGAs, and I don't know. He'll explain a lot of that. We've been working a little bit on FPGA stuff. Gave a talk at Black Hat, and let's see. Dan has lots of experience with messing around with that sort of thing, and that's my intro. So here's Dan Moniz.
Thanks. Nobody hear me? Yeah? Good. All right, so this is the cheap Crac presentation. I'm Dan. Hi, everybody. Thank you for coming to Toorcon. So, I mean, I've already got done with the who, but basically the rest of the presentation is going to go in this format. Who, you've already been there. Why, and then how. And then really the most of it is taken up by how. There's about 20 slides. I'm already ashamed about how many bullet points there are. I really don't like to do bullet point heavy slides. I criticize all my friends at cons for writing slides with tons and tons of bullet points. But I commit the same crime here. Having said that, a lot of what I'm going to have to use the other mic here. I have to move around. Can you hear me? Undo this one? Oh, all right. A lot of what I have to say is more about, I mean, there's points in the slides, but a lot of what I have to say is more about the historical context of the project. And really, it's less about, you know, for people who's heard of Cheap Crac or has heard of Deep Crac, which is obviously the play on the name. Okay, who might have saw the Black Hat presentation, either in person or, all right, one or a couple people. So most of the stuff will be new. We'll figure it out as it goes along here. So what were the beginnings of the project? The project is called Cheap Crac. For people who haven't seen it, I know that the reprint in the program for Toorcon is essentially the same thing I said in the CFP. What Cheap Crac is, or tends to be, originally anyway, was a desk cracking project, and it still is. It began as sort of a random thought experiment. It was a couple of people on a mailing list at the end of last year sitting around saying, well, you know, we're thinking about trying to crack crypto. A couple of people were working on cracking things like WPA, including Hikari. And we were trying to figure out, well, you know, it'd be neat if we could build some kind of generalized platform for this. And to be honest, that's already built. I mean, Hikari and Pico Computing, the company he works for, have already really built a very generalized platform. It's essentially a 4U box that has 16 PCI card slots in it. And each PCI card is just a bus for a PCMCI card bus card. And they make card bus cards that just basically are really fast Xilinx FPGAs with a bunch of, you know, memory and I/O and stuff on them. And those things can be reprogrammed as hardware. I mean, reprogrammed in terms of you can create another hardware design and put it on each individual FPGA and each card and run them really fast in parallel. So for any problem that is parallelizable, like crypto, of course, but also like things like bioinformatics, algorithms, and et cetera, you can do it quickly. But it costs a lot of money. It's not a lot of money. It's, you know, $40,000 or so, but it's a lot of money to people in the room who maybe want to try to do this. Thank you. Yeah, Mancala hour. So what we were thinking about doing was, well, okay, let's really try to go the opposite end of that spectrum. If we accept for granted that $40,000 of really cool Pico computing hardware is badass, but still more expensive than I have out of my pocket now to spend on, you know, essentially just playing around with stuff. What can we do on the extreme low end of that, right? What can we do that's like extremely cheap and is also easy to procure, easy to learn about, is kind of developed with the intention that people are going to mess with it to learn about things. FPGAs in general were already something I was playing with. I had bought a little dev board and had been, you know, messing around with it and trying to get it to do things. And I had been looking into FPGAs mostly by reading about them and by reading about hardware design languages for a while. So I was really interested in finding out, how do I actually build something useful out of this? And out of the discussion, the mailing list said, well, okay, let's just say we want to build a desk cracker. Let's just build that, because we know desk is weak. We know that a desk cracker has already been built. The EFF did it back in 1998, and all of that code and all of those project details are publicly available. So who's seen this book before? All right. A few people, but far too few. Go buy this book. You don't have to buy it. It's scanned and it's available on numerous websites, including Crypt.me and a bunch of other ones. But I highly recommend going and buying it. I don't think it's had a new edition. It's published in 1997. They actually published the book before they finished building the machine. It is all free source content, so you can go and find it online. But I highly recommend buying it anyway. I don't know if the money still goes to EFF or if O'Reilly is pocketing it at this stage, but it doesn't matter. It's a book worth buying and having on your shelf. It came in handy for me because literally I took it off the shelf, flipped 2 pages of OCR-able source code for all the VHDL, and then basically started implementing. This is one example. This is the chip, essentially, that book defines. The book defines a bunch of other things, too. It defines the actual hardware machine and the board this chip is sitting on, but this is the actual chip, the AWT 4500 Deep Crack chip. AWT stands for Advanced Wireless Technologies, which was the company that EFF, John Gilmore, and Cryptography Research, which were all the partners in the project, partnered with to actually fabricate the chips. AWT was a company that fabricated ASICs for small runs. And in this case, the run was like under 2,000 chips. So again, in the context of this thing, I'm not trying to say this is something new. Implementing crypto in FPGAs is a common college course kind of project. It doesn't mean it isn't important or isn't useful. It just means that I'm not trying to say, this is world-shaking kind of stuff. It's also not terribly practical. I mean, if you really wanted to crack crypto, even spending as little money as $40,000 on a Pico computing box is, perhaps not even practical. Not because it's not good, but because if you are serious, quote unquote, about it, you can just, fabricate your own ASICs just like EFF did, but in a secret fabrication facility with people who will never ever leak your IP and who will provide you a chip and a machine that will do it in something like hours or minutes, as opposed to essentially what we'll see as days. I have the $250,000 here figure, which will become sort of self-explanatory in a minute. But really, the whole goal of the project was about self-exploration and community. How can we build a grassroots project that has some kind of target to it? It's not just open-ended. We want to crack desks in a certain amount of time. And we can bootstrap off of all this community knowledge, which is the stuff that EFF did, and also get FPGAs in the hands of people, right? This is sort of a lot of what open source does in the software world, right? Somebody finds a project that is aspiring to scratch an itch they have, and they can contribute to it. And then they, use that, and they proselytize it, and they show it to other people, and it goes from there. This is much the same thing. The problem is that up until fairly recently, say in the last 5 years, or give or take, FPGAs have not been powerful enough, or cheap enough, or dense enough to really be people are going to go out of their way to buy just to play with, just to tinker with, right? You really had to have kind of specific uses in mind, even if those uses were reconfigurable uses, even if you knew you were going to do something with it later. You really had to be into digital design or logic or something like that. Now that's not the case, and this gives a project, who in the room would be interested in cracking desks just for fun? Right, I mean, obviously, a few people would be here if that weren't the case, right? So that's the kind of thing that can kind of appeal to people, and the difference is with you can go to SourceForge, you can download something, you can play with it, you can get a compiler, GCC for free, and you can go. With FPGAs and with any kind of hardware, you need to have something physical, right? So that was another constraint, was to make sure that whatever we wanted to use wasn't exorbitantly, expensive to acquire. But a little background about Deep Crack. Built in 1998. The book was published in 97. I think it actually came out in 98, but it was finished writing in 97. The actual machine was built in 1998, and it cost, at the time, $110,000. They budgeted for around $250,000. But that's in 1998 dollars. So today, that's with inflation about $243,000, and the budget, if you assume the same budget, would be about $289,000. But let's just round up and call it $250,000 and $300,000 each, right? What does that get you? It gets you 1,536 desk cracking application-specific integrated circuits, or ASICs. When I say ASIC, and when in the industry says ASIC, think about is chips, right? Essentially, an application-specific integrated circuit is a chip built to do a specific thing. In this case, it's Crac.mp4. They built a machine which took 64 of these chips per board, and they had 12 boards per chassis, and they had 2 chassis, so 24 total boards, each with 64 chips, 1536 chips. And they put them in essentially recycled Sun 4 470 chassis that ran on VME bus. They just used it as an industry standard. It was easy for them to cheaply build a board of their own design that would take 64 of these chips and have all the electrics basically work. They could just plug it in and slide it into a machine and have it go. So this is one of the 12 boards per chassis. So you can sort of see how it's laid out. And then the VME connector on the far end. Right. Each chip in DeepCrack called search units, 24 search units. And a search unit, if you look at the specification, a search unit is, it's not exactly a full desk core. It doesn't really need to be. It implements most of it. But essentially, each search unit alone cracked 2.5 million keys per second in 98. Right, and that was pretty nice for 98. It's pretty nice now, really. But again, it's application specific, meaning this hardware is not reconfigurable. Right, it's built. It does exactly what it does, and that's it. All it does is crack desks. Each chip, by virtue of having 24 of the units, cracked 60 million keys a second, and they had 1,536 of them working on a problem that is inherently parallel. Right, a lot of times you'll hear people refer to problems as embarrassingly parallel. And crypto is one of those problems, right? A desk is a pipeline. It looks exactly like a pipeline. And so it's easy. There's no data dependency. You can easily put as many of these as you want and scale linearly to get less time, right? You have to run into issues about power and cooling and all those things. But essentially, it doesn't cost you anything to just add another one. You just reduce your time by that much. So essentially, the entire DeepCrack system, both chassis, full of chips, running full bore, assuming no hardware faults. They had some chips built in for redundancy in case one chip decided to short circuit or blow up or whatever, would crack 9.616 e to the 10 keys per second. Roughly, what's that, 92 billion keys a second or so, right? And so that gives you an exhaustive total key space search time of desks. In average, the mean was about 4.5 days. Right, so they estimated they could search all of desk key space in about 4.5 days. Now they used this machine on a desk challenge, RSA desk challenge. I think it was desk challenge 2, and they think they got the answer in just under or just over 2 days to one of the to the key in question. 1998 was so 8 years ago, though. I mean, don't get me wrong. I mean, it's impressive even today for the kind of effort it was, mostly because a small, underfunded, civil rights organization decided to take it upon themselves to build something that the government said was impossible, right? I don't have the quote here, but in the book there's a quote about Louis Freeh, former head of the FBI, testifying in front of Congress about how secure DES is. And I don't want to misquote the book because the quote of the book, although a direct quote from testimony out of the transcripts, I believe the quote he gives is ridiculous. It's something like, oh, nobody could break this in 74 billion years, right? Which I think is a number that's completely pulled out of his ass. Even if you look at the theoretical constraints for DES, I think probably more than that or less than that, but still far longer than anybody would care to bother. But of course, DES is not really that strong. So the goal here was, how do we satisfy all these other sub-goals about getting FPGAs into the hands of people and having people start to work on these kinds of problems, and then from there bootstrap and springboard off to their own kind of thing, but still make something that's plausible, right? And we want to have something that's a plausible target that people are going to at least assume to try in the first place. So the goal was, without doing custom hardware, we don't want to fabricate ASICs because it's really expensive to do it. It's actually more expensive per chip in small runs than it is if you were to make an entire run of Pentium 4s. I mean, the numbers are astronomical at that point. I don't have anywhere near that kind of money. But nonetheless, it's still actually more expensive per chip than it would be if you were actually doing a huge run. We knew we weren't going to do either of those two things, right? Even $250,000, I'm not John Gilmore. John Gilmore is independently wealthy, and to him because he puts a lot of money in good places. But I don't have $250,000 to just employ 2 companies to build me a hardware machine. If I did, I wouldn't be talking. FPGAs back in the day were slower and more expensive by comparison, relatively, and less dense than they are today. And what I mean by that is they didn't have as many logic units. Right? There's a lot of marketing in the FPGA universe about what constitutes performance or the availability of performance. Problems with FPGAs and rating how good or bad they are is because there is no design there. Right? It's easy to say something like, oh, well, a Pentium 4 gets so many megaflops or so many gigaflops of speed, quote unquote, at a certain benchmark. You can't really do that for FPGAs because there is no hardware. Right? It's just essentially a collection of logic units that you then layer your hardware design onto. So what happens is the 2 major vendors of FPGAs, Xilinx and Altera, have come up with their own market terms for how good their various lines of FPGAs are. They have various types of lines, right? They have ones that are really high performance, and those would be things like Vertex 4s in the Xilinx universe. And I think there's Cyclone 2s in the Altera universe. And then they have various other more affordable FPGAs that do less, but they still have some kind of numbers for them. The problem is you can't compare the 2. If you get a number from Xilinx that says, oh, well, this FPGA is a million equivalent, that means supposedly that FPGA has essentially 1 million usable gates, logic gates that you can use to build your design out of. But you can't look at that and then go to an Altera FPGA and they'll say something like, this one has 750,000 logic units. But they're not transferable, right? The numbers don't really mean anything, A, because they're marketing numbers, and B, they're not actually counting the same things in the first place. As it was, I didn't have to worry about any of this because I just found the cheapest but yet most flexible board at the time, which cost me about $150, and it was a Xilinx Spartan 3 FPGA. So it just sort of made a decision for me. And that's the other thing. Hobbyists can now buy this kind of stuff in dev kits, for near $0, over the statistical average. And I'm going to pass around. Yeah. No. Hold on a second. Stay. So feel free to take a look at this. It'll slowly make its way around the entire room, hopefully before I'm done. And if you don't see it before I'm done, just find it, whoever has it, and then steal it from them and look at it. Just give it back to me at the end. This is a really affordable dev kit. It's essentially one board. I have a picture of it coming. And it has a bunch of things on it. One is it has the FPGA, which is what we care about. But 2, it also has some I/O. It has a serial port, a PS2 port, a VGA port, and some other things, some switches and whatnot. And it's essentially a self-contained little dev kit, right? It's nothing super fancy that's going to blow your socks off, but it's enough to play with, and it's a lot of things to touch. And I'm somebody who really thinks that having a physical component to things that are supposed to be exploratory is good, because it means you actually get to alter the state of things immediately without having to have a setup. It doesn't necessarily enter into would I use dip switches to program my desk cracker? The answer is no. But it does enter into, well, if I wanted to make it just, do little interesting, cute things, can I make it do those interesting, cute things just by flipping a switch? And the answer is yes. So again, what was the target for Cheap Crac? Well, the issue was we wanted to do as well or better than Deep Crac, right? We wanted to take advantage of the fact that 8 years of Moore's Law has passed. That affects FPGAs just as much as it affects, CPUs and everything else. Transistor count goes up, right? In the case of FPGAs, what we're really concerned about is logic unit count, right? Transistors or whatever. We're really concerned about just density of logic elements on FPGAs. Notably, I should mention, a lot of people have done FPGA crypto cracking experiments in the past. One of the best papers I ever read, which is actually included in the Cracking Desk book, is by Ian Goldberg, when he was still a student at Berkeley, commenting on essentially a desk cracking machine in an FPGA of the era. It was actually a CPLD, which is a logic device, and they're similar to FPGAs. They have slight differences, but essentially he found an Altera, I think it was an Altera CPLD that he could buy cheaply that he got on a Berkeley program, and implemented a desk cracker, and then made some benchmarks off of what he found at the time. And this is written, I think, in like '93 or '92. It was a fairly early paper. So people have done this before. We didn't want to do any ASICs, like I mentioned before, and a budget of $10,000 US total for the entire project, including any overages or costs or like shipping stuff back and forth to people or whatever. Now each of these things notably only costs around $150 in the model that I bought, right? So $10,000 will buy a number of these. And we sort of expect that there will be some other costs related to shipping things and also to buying other add-on modules, which I'll talk about in a minute. But essentially, $10,000 is a lot of money per person, but not a lot of money for a group of people, right? A group of people can raise $10,000 out of their pockets fairly easily if they can afford, if they can afford $150 for a board for themselves, they can probably afford to spend anywhere from exactly that amount to maybe half of that amount in a cooperative project with other people. And that was really the idea, right? How can we make it essentially micro-funded by a collective, right? Not necessarily a collective in a very heavyweight sense, just people who are interested in throwing money into a kitty and buying a bunch of stuff, and then having these things show up at their homes, and then saying, okay, here's the current state of the project. You now have a board because you put money into the pot. Let's download this stuff off of the website, and let's keep working on it. We also didn't want to have any custom boards, by meaning not just custom logic like ASICs, but we didn't want to have to create a custom board. We wanted it to be a commercial off-the-shelf development board. There's two reasons for that. One reason is you can buy them now, right? I don't have to do any work to make a development board. I have to do a lot of work to make a custom board. I have to have my design already explained. The other issue is that once you're done with Cheap Crac, or if Cheap Crac bores the hell out of you, you have something you can go do something else with, right? The immediate thing that when I first got, as the board moves around, people will notice it has VGA out. And one of the first things that I thought about doing when I got it, way before I ever thought of Cheap Crac, was implementing old arcade games, right? The first thing I literally thought about doing was I can implement Zaxxon on this thing, right? And not only does it have VGA, which is good, but it also has PS2. And the PS2 can either be a mouse or a keyboard. And I was like, sweet, breakout. So let me move on. So this is a picture of the board. As it comes around, you'll see it. I'm going to point out a few of the elements here. When you find it or when it makes it your way, you'll be able to touch it and play with it. This is blown up, so I apologize for the lack of resolution. But essentially, this is the board. It's made by a company called Digilent, which is just a small little company, I believe, out of the Pacific Northwest, and all they basically do is make various types of development boards for people. They make them for industry, people who want to actually prototype, real quote-unquote hardware designs as opposed to, my little toys. But essentially, this one is, this is a particular model. They call it an S3 board in their catalog. If you go to Digilent Inc., notably, if you go to digilent.com, it's some completely other different site. I don't think it's porn, but it's not what you want. But go to Inc.com if you're interested. I picked them purely because, honestly, I had a personal recommendation from a friend of mine who was looking at FPGA boards, and he said, oh, check out this site. You might find something that you like. And I looked. There are a number of other sites. I don't want to shortchange any of the other people. There's another company called XESS, which has a huge reputation in sort of the bedroom FPGA hacker community for being a guy who has put together really cool dev boards. I haven't used any of his stuff, though. This is just the one that I happened to buy. So, here, this is the power. I believe this one is, I want to say that is VGA and that's serial, but I would have to actually look at them. And then you'll notice these three black connectors on the sides. These two on the top and one on the far end. Those are actually peripheral connectors for their own kind of little peripheral interface. And they make a bunch of other modules. And one of the modules they make is this little module that just includes a little USB port and a USB controller. And this just plugs in essentially to the. I'll pass this around also. So, the adaptability here, granted these little ports are not standard in any way. You have to buy their little boards that plug into them, and they transfer power and control and everything else. But nonetheless, you can do things insofar as you can find a board that they've made that already does it. And they have ones for USB, which is the one being one for Ethernet. They have one that will actually do 10100 Ethernet controller on board. So you can plug this into a network and do things with it. They also have one that I believe they have one that does like different kinds of composite video in and out and whatnot. So there's little things like this that people have made, and frankly, it would not be too hard to they publish all the specs. Notably, the other reason I bought a dev board as opposed to making a custom board is that everything is labeled, and this is huge if you're playing with this stuff for the first. to know what everything is just by looking at the board, right? You have a spec sheet, and you have a diagram and everything else that you would normally have. You have a data sheet for all the logic elements and all the ICs and everything on the board. But you can actually look at the thing, and while touching it, figure out what something does, right? As long as you can read English and understand abbreviations, you're pretty much well set off. Other things, there's 4 momentary switches. These are just little push-button switches that don't stay down. They're just momentary switches. And then it has 8 little flip switches. These are settable that you can use to control. These are all I/O elements, right? You have to make these do anything. They don't do anything natively, just like none of this actually does anything natively. But you can make these things do things. So one of the things I first thought about was, well, it'd be neat to like have different combinations of these switches program the thing. And you might make your own little like 8-bit computer or whatever. But in the context of Cheap Crac, all we really care about for this right now is the FPGA, which is in the center over there, where all the traces you'll notice lead to, and that's as this comes around, you'll see actually how big this thing is, but it's essentially the size of a postage stamp, right? This particular model, which you can't read from here, but as you see the board come around, is an XCS 1000. What the 1000 designator means is that it has a 1,000,000 gate equivalent. They make a 250 and a 500 also, which is roughly like a 500,000 gate equivalent or a 250,000 gate equivalent. And then, oh yeah, the LEDs, of course. Always need LEDs to do stuff. So I realized that this slide doesn't make any sense. It'll make sense in a minute. As I went through this, I didn't really find anybody who had done a modern quote-unquote FPGA implementation of the same desk cracking project. There was the paper from Ian Goldberg. There were papers that were mostly not implementation papers, but calculation papers done in the early and into early mid-90s, where people would estimate how much computing resources it would take, or what their prognostication for an FPGA would be for doing this kind of stuff. Ian Goldberg's paper actually did implement, but it was fairly old. So then I recently came across a paper by this team in Germany, and they built this thing. And the only reason I say it's the Germans here is because they really rocked out, and it kind of depressed me because it's like, oh man, they got there first. But yes and no. We'll see in a minute. So this is what they built. I swear to God that they did not know what I was doing when they made the title of their paper. They built this thing, and they presented it at the Sharks Workshop in Cologne earlier this year, called How to Break Desks for 8,090 euros, which was just, it kind of drove home one key point to me about the entire project. And this is the thing that I think is the most interesting revelation from the entire effort, is now a race to the bottom to figure out who can crack desks, right? It used to be a race to the top, meaning the way everybody used to look at the problem was how long did it take to crack desks. Now the issue is, oh, I can do it in 8 days. Oh, I can do it in 7 days. It's a race to the bottom. Cracking desks, a former federal and to some extent global encryption standard, is now a race to the bottom, right? And that's like hugely profound compared to where we were, years ago. So, in order to justify my continuous existence in this project, I will note that as of today, the screenshot from xe.com still shows that 8,090 euros is more than $10,000. But notably, they did, as you can kind of see in this picture, fabricate their own kind of modules here. But okay, so they call it Copacabana. They made like this constructed acronym out of a cost-optimized parallel code breaker, which is essentially exactly what Cheap Crac was. Cheap Crac was just a play off of Deep Crac, but yeah, cost-optimized, right? And this is the thing about hardware design. Unlike software, where you design for things like how fast does the UI respond, how many photos can iPhoto load, or things like that, you have constraints, but they're all very fungible. You can make trade-offs on CPU time versus memory access and things. In hardware, you have a lot of constraints as well, but a lot of times you can't really trade off quite as much, right? If you have an FPGA with so many logic gates or so many logic elements, you have only that many, right? So really, you have to optimize your design. So the part to mention here is that the constraints are low cost for both of us, for both Copacabana and Cheap Crac. The issue is do it really cheaply. Now, notably, they are people who actually know what they're doing. I am a complete dilettante at this. I admit it fully up front. about FPGAs and VHDL and digital logic. I've read from books and have learned from tinkering with stuff and failing, and failing. Whereas these people actually, went to university and have some amount of quasi-corporate infrastructure backing them up. It's not a lot, but they know what they're doing. I mean, they've actually learned it in a real setting. So what is their hardware? I want to talk about their hardware for a minute because it has a lot of relevance to Cheap Crac. Their hardware uses Xilinx Spartan 3 3S1000 FT256 FPGAs. This is the exact same FPGA that's on the board in the room. Right? They're using the exact same model and the exact same mount. Right? It is identical. Granted, they do mount 6 of them on a DIMM. So they built a little DIMM, and they mount 6 FPGAs per DIMM, and they just use the DIMM as a holder. It's just a little module, basically. And so the way that they built it was they have these FPGA modules that they just slide into a backplane. And they built a backplane that has 20 DIMM slots and little bits of controlling logic just to handle the bus. So their total setup is 120 FPGAs. So keep the numbers in mind. We went from 1,536 custom circuits, custom chips, to 120 FPGAs, right? Well, what do they get? The entire device, meaning all 20 slots, each with a module, each with 6 FPGAs, so 100 FPGAs running in parallel, does 48 billion keys per second. Okay. Each FPGA has 4 desk cores. So each little chip on their module is actually running 4 independent desk cores in parallel. Right? Their average exhaustive key space search is 8.7 days. Right? So we went from having it being able to be done in around 4 days, give or take, right? 4.5 days, with custom hardware and $250,000 to being $11,000 and essentially 8.7 days, right? And college students. This is roughly equivalent. They benchmarked a DES implementation that they had on hand, and they benchmark it that this is roughly equivalent to 22,865 Pentium 4 3 gigahertz cores doing nothing but cracking DES, roughly at around 2 million keys per second all day, right? They estimated, like, I think, roughly they say their thing is 400 times faster, right? So if you had 22,865 Pentium 4s at 3 gigahertz cracking DES, you could get around the same average search time. And this is what their little device looks like. Basically they have some power, and then it's really just a complete, all it is essentially the same thing. They could build another one of these things and link them together, and they actually mentioned this. They have another port here, but they actually mentioned in their paper that you could have another module. They call one of these entire things with all the slots filled up is one Copacabana. So you could have another one of these linked to it by USB, and then decrease your search time by half, and so on and so forth. It's a really well-designed architecture. I haven't seen it in person. They presented it at a Sharks Workshop in Cologne, and I haven't been to Cologne. So, now all of this made me really sad. I was really kind of hoping that it would be a neat project that I could get a lot of people into by virtue of talking at conferences like Toorcon, and also by virtue of passing around things and showing cool demos. I also understand that people don't really want to work on stuff that's been done before. So Deep Crac was done, but Deep Crac's a different thing, right? Deep Crac is a serious engineering effort done by unexpected parties. But replicating that as bedroom hackers would still be a neat project. Copacabana brings it closer to home, right? They do as well or better than Deep Crac for way, way less money. And it's so close to what I'm trying to do that it's almost like, well, why would I bother, right? Copacabana is really practical for desk cracking, and it's really practical for cracking in general, any kind of parallel problem you might have. So desk cracking, they mentioned in their paper some other issues regarding elliptical curve stuff and some bioinformatics algorithms they want to port to it. Essentially, they're just reprogrammable hardware, just like anything else. So anything that's parallelizable, you could use Copacabana to do cracking, which is the thing that they targeted first. DES is an easy target. Again, it's a race to the bottom. So because of that, it's really practical for that kind of thing, but perhaps it's not as practical for other things. One is, it is also a custom fabrication job. So although they are using a commercial off-the-shelf FPGA, you have to make their DIMMs and plug them into their backplane and everything else. It lacks certain things. Cheap Crac as an effort, I think, is still worthwhile. It's a grassroots effort, and again, it's more about community than it's about cracking. Right? Cracking desks is so easy now that it's almost trivial, right? I mean, $11,000, if you were really interested in cracking desks, $11,000 is not hard to acquire, right? I mean, people with mob ties would sneeze $11,000 at you to be able to read email if it was encrypted with DES, right? Furthermore, it gets FPGAs into people's hands, which is really another huge point, right? It puts hardware in people's hands who, after they've decided that Cheap Crack bores them, or we succeed for some definition of succeed or whatever, they can go do something else, and that can become a project. And then when they want help on that project, if they want to attract other people, oh look, there's a community of people who already have the same exact dev board, who have experience working on the project, who have done something with it. So, where is Cheap Crack today? Well, the board is being passed around, so you'll see it. It's an alpha, right? And I sort of told myself that regardless of the status of Cheap Crack at any given point, the first talk I gave about it would probably also be the last, only because I don't really like repeating the same talk every time I go to a con. But having said that, I can attract people into it, or if people like it, or think it's interesting, or even if somebody says, well, you know, Cheap Crack is a neat idea, but maybe you really should target this other thing, that's totally cool. And then everything else after that will be a birds of a feather kind of presentation, right? One of the things I am interested in doing is getting help on the project to either redefine it further or to continue to work on it. I think it's still interesting to work on. There's a lot of information to take out of what the Copacabana guys did in terms of how they implemented their cores and all this other stuff that would be useful for Cheap Crack. And it's still to have a bunch of people, you know, who are all in this room who are interested, essentially put together a desk cracker that can still do it in 8.7 days or better. You know, if we can do better, we can do better. So what are the details? Well, we started with the EFF code, and that was just an economic decision, right? It's cheap to start, it's freely available, and we know it's there. We can get it, and we can just plug it in and use it, right? But we also understand that it is built essentially for 8-year-old technology, and it is built for ASICs, not FPGAs. So they don't really have a constraint quite so much about the number of logic elements. They can just write a hardware design, right? And then they'll just end up with what they have. So the issue was that when you try to apply it to FPGAs, you ran into these serious resource overuses. In the FPGA design universe, when you use too many of a resource, it's called a resource overuse. And essentially it means that you have to refactor your design to use only the amount of resources that are available on the chip. It's a simple design. It works fairly well. We know it works because it actually did crack DES in 2 days, but it needs tailoring to FPGAs. The University of Leuven in Belgium has a really fancy implementation that I really want. And it's actually the same thing that the Copacabana guys used. It's that 4 desk core, pipeline desk core in 1 FPGA. And furthermore, I know it works on that exact FPGA that I have because that's what they're using. That's what they developed it for. Right? So it's a drop-in badass desk core. If anybody knows anybody at the University in Belgium, have them get in touch with me. What is the target performance for Cheap Crack? Well, I mean, we're going for the same thing that the Copacabana guys did, because really, if we can achieve the same performance with the same FPGA, we should be able to, right? The target is around to be able to crack 400 million keys a second at around 100 megahertz, right? Which is some numbers that they've also seen at that particular clock speed. The XC3S1000 has a maximum clock speed of around 300 megahertz, but you want to be careful about overclocking FPGAs because there's nothing to stop you. And what stops you is a situation called thermal runaway. And thermal runaway is basically where you've clocked it so hot that the thing melts. USB connection back to controlling PC, that's a standard thing. That's how Copacabana works. And that's why we picked the USB modules, is it's easy to plug in and go. USB is a fairly simple protocol. We don't have to do anything with Ethernet frames. And it's also like everybody has USB, so it's like not a big deal. Things that was always a design constraint was to have people, to have the $10,000 could have be gathered together, and then to have it used to buy hardware to send to people who were interested. And the idea initially was that as many people as got boards would come together at a given convention, and we would take as many people who were there and build the desk cracker live at the con. Right? And if you had enough people and enough boards, in theory, you might actually even do better than 8.7 days. Right? You might actually do a lot better. But that was to kind of have a build fest or a flash mob kind of build effort, right? Just have everybody show up, bring their board. We all have the same, image. We have some support software, and you just go. So what are some of the to-dos for Cheap Crack still to come? Well, this is the thing I mentioned, right? The Copacabana doesn't have like a VGA output on its board, so I can't do any sweet ASCII art, which is a problem. All crypto cracking devices these days need sweet ASCII art in order to be acceptable to conference providers. Um, so it's already on the current dev board. Notably, we don't have to stay with the current dev board. The company that I mentioned has released a series of other dev boards, some of which may be better at the same price point or slightly more expensive. It was just the one that they had at the time that was like the easiest to buy and also like the best to use. There is an Ethernet module as well, which would be cool because we could plug it in, and then if we wanted to, we could not only control it over Ethernet, which would be sweet, but we could also use it network desk cracker, right? So of course, one of these things with an Ethernet module would not be terribly exciting because it would still take longer than you would see the packets go across. But a lot of these things network together, all cracking simultaneously, and maybe capturing and storing and caching the traffic and not just letting it pass through transparently, and then crunching on it. If I can crack in around a couple of days or even less with a lot of them together, then actually having just a little network tab might be interesting. And if anybody's still using I mean, I used to use desk login way back in the day. If anybody's still using it, I mean, obviously that's one target was off the top of my head. There's tons of other things you could think about. And then a better customized desk implementation would be useful, right? I mean, I want the University of Leuven stuff, but it would also be neat to, one of the reasons we picked the EFF code in the first place was because we could learn from it, right? We'd have to learn what it all meant and then figure out how to apply it to FPGAs. The University of Leuven stuff would be closer to the environment we have right now, which means it would take less learning time, but would because they've done a lot of work on the algorithms, so we'd have to figure that out. That's the end of that. So from now on, I'll take any questions. I have about 15 minutes. Yeah, Tom. Okay, so the question is, how many blocks does it need every time it tries to decrypt a key, and how does it know that it's getting serious of garbage? How many blocks does it need to try a key? It depends on the design. The things I've seen say about 16 blocks. Like basically, essentially, you have to take the key, pad it if it's not acceptable to the function, and then send it through. In terms of getting plain text, so one of the things that's not mentioned here is that DeepCrack and all the other projects, including Copacabana, all rely on PC software or software running on a separate host, actually controlling whether or not something is valid. So what EFF did, DeepCrack, was they had some software that essentially looked at all the return responses from the desk cracker and filtered out ones that were totally garbage. And then essentially they only raised alerts for things that were possible matches, right? So they looked for things like if it has any high ASCII, right, it's not a possible plain text, right? I think that they had some definition of what plain text was in the challenge that they broke, and I think the definition was it was only going to be ASCII. So if you have any high ASCII, that's not valid, right? If you have any combinations of numbers or letters that wouldn't be words, that wouldn't be valid, right? So you do have to kind of know or have some guesses as to what the plain text is. But of course, because otherwise you have to re-encrypt every single time and figure out that. But all of them work on a controlling piece of software. Does that answer the question? Okay. Yeah, go ahead. You probably could, and I don't know. I think the reason that EFF didn't do it the way is because, well, they might have actually implemented that in part of the throwaway. I don't know if EFF's whole design was based on the idea that let's just do the simplest possible thing that can work, that is the least complicated. Now that seems to me something that would pretty readily occur to somebody like Paul Kocher. So it's quite possible that they did, and I just haven't read into it. So anyway, yeah. So the person who actually wrote the VHDL code is a guy named Tom Vu, who I haven't had a chance to talk to, but want to. I think it was just because that's what AWT knew. Yeah. I personally only understand VHDL purely just because I haven't taken the time to learn Verilog, and it's one of those things, right? There are some slight differences, but essentially they both describe the same functionality. So I think a lot of people in the room, if people who here has played with FPGAs, I never asked. Right. How many people out of that group of people, keep your hands up, are Verilog hackers? How many people are VHDL hackers? Sweet. I'm in a minority yet again. I literally learned VHDL because I found a really good book on VHDL that was cheaper than all the other books I could find on Verilog. Basically, I mean it's all economics. Somebody else had a question. Anyone else? Way in the back. How much? So the question is, how much RAM does an FPGA have? Isn't that a limitation? Potentially. So some FPGAs don't have any. In the case of this, I think the block RAM on the I don't remember. Do you know what the block RAM is on the Spartan 3s? Yeah, it's really small. Is it a limitation? Not practically. What you do need is SRAM to store the image. Things about FPGAs typically is that because they are reprogrammable, they literally are loading their design from some source, right? So you have to have what's usually called platform flash, which actually stores essentially whatever the hardware design is in a little piece of battery backed up flash, and then that gets loaded into the FPGA. This is different from say CPLDs. CPLDs you can kind of turn off and lose power and then come back and they'll be alive. But FPGAs need to load their hardware design from something. It's essentially loading code. The reason I split it up is because hardware design is not really like programming. But does anybody in the room who's done FPGA things, anybody have any insights as to good statements about how programming and hardware design are different? I'm always looking for ways to explain it to programmers because I'm trying to convince them to learn it. But yeah, way in the back. Go ahead. Right. So yeah. So one good example would be that code is built around instructions for a CPU, and FPGAs are built around built around logic units. Yeah, it's true. And then, the thing that I've taken to saying is like, imagine writing software is more like writing a description for how you're going to sweep a room in the house, and writing an FPGA is more like actually plotting out the pathways to be swept. Right? It's a really bad analogy. It's the best one I've come up with so far in the front. To drawing circuit diagrams. I've only written VHDL. So what you write in VHDL is essentially a description of. Do I have any VHDL I can show on this? I don't think I have any VHDL that I can show on this laptop. VHDL is essentially what you describe are a number of ports, and then what those individual ports are and their behaviors. And Verilog has a similar model. It's slightly different. For people who understand Verilog, I would love for somebody to explain how Verilog does it. But VHDL, so VHDL is a subset or a superset of Ada, and it was originally designed because Verilog, when it first came out, was proprietary. They're both open now. It doesn't really matter. As far as drawing circuit, you can derive a circuit diagram from VHDL, and in fact, that's what a lot of FPGA, as almost all FPGA software does, either behind the scenes or can also provide you a graphic representation of a system. And they basically, it's all just block diagrams, right? So it's like input to this, clock to this, right? Reset to this, whatever. I've not done any of. I have looked at some of the graphical kind of like grid, or not grid, but like graph flow kind of hardware design languages, and I haven't really played with any of them in any kind of serious way. But essentially, HDL, you're really writing a spec essentially for how a circuit works. So like the inputs, the outputs, and then like clock rate and speed and voltage and all this other such. And then you basically you can define elements. And in VHDL, it's great because you have this library of stuff, which I'm sure is the case in Verilog also. But you have a library of things like standard logic, and so it includes things like op amps and NAND gates and all this other kind of digital logic elements that you use to build things like memory or whatever, right? And then eventually, when you synthesize it all together, it builds what's called a netlist. And a netlist is actually what you end up putting, essentially on. You make the netlist into an executable form for the FPGA. A netlist basically describes a graph, really, and it's essentially called a netlist because it describes the interconnection of all the wires and all the signals on the wires. And then you basically load that into some kind of format. Each vendor of FPGAs has their own essential program format. They feel declarative to me. The question is, do the languages feel? I can't speak for Verilog. From what I understand of Verilog, and what I've read of Verilog is it's a lot more C-like. So if you're familiar with C, Verilog is a lot easier to pick up. The things that I like about VHDL, and again, it's speaking from a complete area of ignorance of Verilog, really, other than what I've read about it, is that VHDL seems like it's more tailored to building systems. If you wanted to, Verilog, I think it's really quick to like write like a specific circuit or a specific kind of design, like quickly. But if you want to build a system, it seems like you require a little bit more support in Verilog than you do in VHDL. On the other hand, VHDL, it's a lot more heavyweight to like build little one-off things, right? I think they're declarative insofar as, yeah, I'm actually literally saying, object S1 is a, NAND gate or whatever, right? Like I'm literally saying essentially these things are these things. And then you basically have to describe the behavior of these things. So how do they actually take signal in or process input or whatever else? To me, it's different from programming because programming is very abstract. I mean, even at the assembly layer of programming, you still are just referring to things by names, like registers, right? Like R1 or EAX or whatever, right? It's still an abstraction, right? You have no idea really where this stuff is. I mean, it's in the CPU somewhere, but you really have no idea. With hardware design languages, you absolutely know where it is, and you're going to put it there later, right? You're going to plot it and map it and route it and everything else. Yeah, go ahead. Right. Right. Yeah, and the simultaneous is a big point. So one of the point being made was that in VHDL and in Verilog and hardware design languages, you're really thinking about everything happening kind of simultaneously, whereas in at least in imperative programming languages, everything happens in statements. My other counterexample would be I'm a functional programming language geek, like Haskell and Lisp and all that kind of stuff. So I think about evaluating arguments all the time. But no, you're right. And I think the biggest thing that I had to learn when I first started doing hardware design was parallelism, how to parallelize problems. Right? You really have to break things down out of because you can really easily create like a hardware design that's like one wire, right, with a bunch of stuff happening on one wire, and then at the very end of the wire something happens, right? Like you get some output. It's a really inefficient way to do things, though. It's very straightforward from a sequential kind of imperative C kind of mentality of doing things, but it's really inefficient if you're actually looking to use all the hardware you have available to you. So figuring out how to build parallelism into the problem is a thing that I had to think about a lot. Any other questions or comments, anybody? All right, thank you. I have about 5 minutes before I have to leave the room, so everybody can feel free to come up, and then as long as I make sure I get the boards back, that'd be great. Thanks.